let's look at a couple of the key problems from the test. This was the one that most people had trouble with. How do we find the length of segment AE, which is, now if you think of this as being, small, medium, and large triangle, AE would be sort of the left side of the large triangle, right? How are we going to find that? What do you think there?
We do like 4 to 6 equals x4 on the other side.
Okay, yeah, we could. Probably the easiest way to do this one. Some people tried to maybe do this as a ratio of triangles, but that doesn't work well here because we don't have all the information to make that work, right? Now, like if we were doing a problem like trying to find, for example, FC, that would be an easy one to do using similar triangles. If we were trying to find FC, we could say use the medium and the small triangles. And if we call that x, I want you to see the difference. If we call that x, I could say like x over 3 equals this whole distance, which is 10, over 4, right? Does that make sense? Big to small equals big to small, right? Cross multiply, be done with it. That'd be easy, right? Can't do that here, though, because we don't have, like if I use the small triangle, for example, I don't know what that side length is, right? So we got to do something a little different. Well, Theron had a good idea. Why don't we use the properties we have from 8.6? We know if I just ignore the whole top of the triangle here and just focus on, for example, the small in the middle. Now look what I've got. I've got a side that's a line that's coming through and cutting through the triangle parallel to one of the sides, right? And if it does that, it's going to cut the triangle proportionally. It's going to cut the triangle so that segment over that segment equals that segment over that segment, right? I'm able to set up a ratio pretty easily there. I could say something like, if I call this distance down here x, I could say 4 over x equals 6 over 4. Does that make sense? And that's a good little trick. That saves us a lot of time. So if we do that, I can just cross multiply and get 6x equals 16, so x equals what? What do I do to get the x by itself? Divide by 6. Good. So 16/6, which equals, if I reduce that, 8/3. Okay, good. So I could go ahead and write that number in. We've got that one now.
So now what you do is find each one and get the whole.
Yeah, find each one, and then we'll just add them all up. Good. So this is 8/3. And now we'll go up and find this guy. How about? We'll call that x. And we could do the same little trick. Okay? Yes, sir. Okay. Now we'll just ignore the stuff down here, and we'll take this example where we've got 3 parallel lines cutting across 2 other lines, transversals, right? And if we do that, here's our, so we got this line, and this line, and this line cutting through these transversals, and we get the same kind of thing going on. Right? Now we know that this segment right here divided by that segment equals that segment divided by that segment, right? Cuts them proportionally. So I end up with, if I'm solving for x, for my second x, let's make this a red x, how about? I get x over 4 equals what? 5 over 6, exactly. Cross multiply. 6x equals 20, so x equals 20 over 6, which reduces to 10/3. Okay, and I can just write that in. Now I've got them all, 10/3 plus 4 plus 8/3. Remember, you've got a handy little helper in your calculator here. It's going to tell you, if I add fractions in here, it's going to give me maybe a decimal answer, but I can easily convert that into a fraction if I want to. So if I add all those up, 10 divided by 3, that's 10/3. plus 4 plus 8/3 equals, well, this one works out pretty nicely. It works out to be 10. Okay, so that's the answer. Now, what if, let me just change this last one a little bit. What if we had instead, I'm going to show you something cool here. What if that had been, say, 10/3 plus 4 plus 7/3 instead? Okay. It would have given me a weird decimal, but if I want to turn that into a fraction, how do I do it? Math 1. Convert to fraction, enter. Look what it does. 29/3. Select. Okay. Questions on that? That make sense? Okay. Okay, find the measures of the angles in a triangle. Okay, we're told the measures of the angles in a triangle are in the extended ratio of 4 to 7 to 9. Find the measure of the smallest angle around the near side. Okay, so now if numbers are in an extended ratio, that just means it gives us a lot of information. It tells us the ratios among all three instead of just two, right? So what are some examples of numbers that would be in that ratio? Well, 4 to 7 to 9 would work. What's another example of three numbers that would fit that ratio? 8 to 14 to 18. How did we get those? Yeah, we just multiplied all the first ones by 2. What's another one we could get? What if I multiplied them all by 3?
12, 21, 47.
And I could do that forever, right? Now, those all fit the ratio, but for us, we have to get some specific answers because they have to fit inside of one triangle. So what must they all add up to if those are the measures of the angles in a triangle? 180. So we've got to multiply each of these numbers in that ratio by the right amount so that they all add up to 180, correct? Now, we don't know what to multiply them by. We could try this forever and never get the answer by trial and error if it's some weird decimal answer, right? So we can't just sit and do trial and error. That's where we've got to do some algebra. So if we don't know what to multiply them by in algebra, you guys are getting good at this. That means that's our unknown. So what are we going to call it? X. That's the variable, right? A variable and an unknown, they go together, same thing. So we'll take this ratio and we'll change it into 4x, 7x, and 9x, because that still fits the ratio, right? We've multiplied all three of those numbers by the same thing. We just don't know what that is yet. But we can find out by just adding all those up and setting the sum equal to 180. 4x plus 7x plus 9x equals 180. Let's solve for x. What do I do? Okay, combine like terms. So all those 11x plus 9x, there's our 20x, is 180. Divide by 20, right? So I get x equals what? 9. Okay, now we want the smallest angle, so which of these is going to be the one we want to plug the x back into? 4. And 9 is not our answer, right? A lot of times people just input that and thought they were done, but they're not. This has to go back into that guy, right? So the smallest angle is really going to be 4 times 9 equals 36 degrees, right? So that's what we would put in the answer box. Okay, make sense? Okay. Okay, this one. Triangle ABC is dilated about the origin by a scale factor of 2/5. Find A prime, B prime, C prime. Very simple. All we do, if we've got the scale factor and we're doing a dilation, that just means all the distances from the center, from the origin, are going to get multiplied by that amount, including the coordinates, x and y coordinates of all those points. So all I've got to do, let's find what those coordinates are. What are the coordinates of A? -5, 4. B is what? And C is -2, 1. Okay. -1, right. -2, -1. So we'll just take each of those original coordinates, so those ordered pairs, and multiply the x and the y coordinates both by our scale factor of, well, how do we write that as a fraction? 2 over 5. Okay? Right. So if we do that, so a starts off as negative 5, 4. To turn that into a prime, we're just going to multiply negative 5 over 1, right, times 2 over 5. You just multiply by the fraction 2/5. If we're going to multiply by a fraction, let's put a 1 on the bottom. Make things a little easier. And that's going to give us the x coordinate. Well, what is that? If I multiply straight across, right?
Negative 10 over 5.
Negative 10 over 5 reduces to negative 2. So that's going to be the x coordinate of A prime after we dilate it. Okay, what about over here? Now for the 4, we're going to multiply 4 over 1 times the same scale factor, 2/5. If I multiply straight across, what do I get?
8 over 5.
8 over 5. And that doesn't reduce, does it? So 8/5. Okay. Get the idea? We could do that for all of them. Should we do it for one more? Let's do B also, how about? So we got B as 3/4 initially. So we start off with B having coordinates 3/4. If I want to convert that into B prime, I'm just going to multiply 3 over 1 times 2 over 5. And what do I get?
6 over 5.
Okay. So that turns into 6/5. Okay, so that goes here, because that doesn't reduce. And then over on the other side, we've got, we already did that, right? 4 over 1 times 2 over 5. That already gave us 8/5. Okay, see how that works? We just do it for all three. And we got them. Okay. Questions? Good? Good. All right. Okay, identify the dilation, meaning is it, what are the words they use? Enlargement or reduction?
Yeah.
Meaning to get bigger or smaller? Okay. So is it enlargement or reduction? Well, what is it? Reduction. Good, because we always end with P prime, so we must be starting with the big shape, and it's going to be moving towards shrinking and all moving towards the center of the dilation at the same time, right? Okay, so it's a reduction. We got that. Because it's getting from big to small.
Oh, the little triangle inside of it?
Yeah,
Okay.
right. Okay. Now we want to find the scale factor. Remember, there's two ways to do that. We can always take a ratio of corresponding parts if we know the measurements of two corresponding parts, which we don't here, right? All I know is that that's 7, but that's x. That's not going to help me. 7 over x, I need a number. So the other option, though, the scale factor is the ratio of corresponding parts, but it's also the ratio of distances from the center, right? Corresponding distances. So P starts off a distance of 18 from the center and ends up, P prime, being a distance of 10 from the center, right? So I could also do that. I can use those measurements for the scale factor also. So then the scale factor, K, is going to equal what? So 10, right? It's got to be the P prime one. That goes on top always. So, it's the final divided by the starting values. So 10 over 18, which is going to reduce to what? 5/9. Okay, so the scale factor is 5/9. 5/9. Right? Make sense? Now we can check that. You should be one thing that I don't think people do enough, I think partly because it's so easy to retake tests and things, but, you know, it's still, there's not that much time now. Now you really got to be a little more careful. Ask yourself before you just hit submit and send it out there to the chance, is my answer, does it make sense? Does 5/9 make sense in this context? Is that a reduction? Yeah, it is, right? The scale factor would be less than 1 for a reduction. It's going to make things smaller. Well, that's a fraction less than 1, isn't it? Now, what if I had mistakenly put that the other way, so I ended up with 9/5? Red flag, right? Does that sound like a reduction? No, no, no. That would be an enlargement. If I wrote this as 9/5, that fraction is bigger than 1. So therefore, that would be an enlargement. And we know this is a reduction, right? So we know that first number has to be smaller than the second number if it's a reduction. Okay, and then finally, how would I solve for x? I've got my scale factor, right? Now that's telling me the ratio of small to big, right?
So you equals 7, right?
Yeah, exactly. Because I can see here that 7 and x are the lengths of corresponding parts, right? So I just want to do small divided by big, because that's 5/9 is small to big, right? And if I cross multiply, I just get what? 5x equals 63. So what's x? 63 divided by 5. Okay, and I think the instructions aren't here, but I believe this is one that says don't round. So we put that in as 63/5. Now that actually would be a terminating decimal, so a decimal would work for that one. That would just be 12.6, so that would work. But sometimes, you know, we will need the decimal, or we'll need the fraction if the decimal doesn't stop to terminate. Questions? Okay. All right, we're moving. Okay, this is a really easy one that a lot of people miss, and so I want to take a second and rehash this stuff. If we want to simplify the ratio, we have to be comparing the same kinds of units. Right? If I did something like 1 mile divided by 2 inches, well, that's going to give me a numerical ratio of 1/2. But does that make sense? I mean, if we think about the actual distances, isn't a mile a lot bigger than 2 inches? So that fraction should be a heck of a lot bigger on the top than the bottom if I turn the units into the same thing. So all I've got to do here is convert these units. This class isn't really about converting units, and so I don't mind even giving you a sheet with all the conversion factors on it. That's, if that's helpful, that's easy to do. How do we convert? Well, what do we convert here? Which one gets converted? Yeah, good. Always convert the big one to units of the small one, right? So how many, what would I do to that 1.5 meters to convert it into centimeters? Yeah, how many are there?
2.
How many? So we're going to move it 2 decimal places, 100 centimeters in a meter. So we'll move the decimal 2 places. So this would equal 150 centimeters over 80 centimeters. Being as I'm comparing centimeters to centimeters now, the units are the same, I can ignore them. How do I reduce that? Divide by 4. I could even divide by something bigger. 10. Now here's the trick. If the numbers end in zeros, both of them end in zeros, I can always cancel ending zeros, right? So I can do that. That's the same thing as dividing by 10. Doesn't that make sense? 150 is to 80 as 15 is to 8, right? And I can't reduce that anymore, can I? So my ratio is just 15 to 8. Okay? Now remember, real quick, what's going to happen? What if we had gotten a ratio of like 15.6 divided by, divided by 4? How would I reduce that one? I got a decimal in it, because I can't have decimals. These have to be integers. Move the decimal. I'm going to multiply both by 10, right? So I could turn that into 156 over 40, right? So I got to move that decimal over also. That's really 4.0, right? And then I could reduce that number from there. Okay? Make sense? Okay, these triangles have to be similar, true or false. True. How come?
Because the sides are.
Okay, the sides are parallel, right? And they share an angle. So if those sides are parallel, I mean, if I pull these triangles apart, they obviously share that angle, don't they?
Yes.
If those lines are parallel, then Theron, what's going on?
The parallel lines cut the segments they cross proportionally.
Okay, that's another thing that's going on. Yeah, we could set up proportions and use side angle side. But we could also just do this. I know that if two parallel lines cut through a transversal, corresponding angles are congruent, right? And so I would know that that angle, if I pull those apart, I've got this angle and this angle in both the big and the small triangles would be congruent. And so by angle similarity, they're similar, right? Okay, so that's true. That's true. What about that one? Yeah, it's not going to work, is it? That's clearly not going to work. Because what I would have to, and you know what, it couldn't work in any circumstance. Even if those other sides were proportional, there's no way for this one to work because none of these three similarity relationships could apply. If I line these triangles up, so I've got this one, and let's see, so 72, and let's see, that would be, all I have to do is kind of tilt this one a little bit. Is that right? Everybody agree? Let's color code the sides. So this side would match up with this side, right?
Yeah.
And then the one opposite the 72 would match up, right? And then the green sides would match up. Well, let's look at our options here. Could we use side, side, side?
No.
No. We only have two sides, right? And they're not right triangles, so I can't use the Pythagorean theorem to find the other side, right? So that one is out of the question, right? That one's no good. Can't apply. Could side angle side apply? No, it can't. Because even though these angles are congruent, for me to use side angle side, I would have to know that the ratios of the red and the green both followed the same proportion, right? But I don't know the green sides. So even if, I mean, these don't work, but pretend they did. Pretend that this was a 9 and that was a 10, and this was a 20, and this was an 18. So that those ratios held. Everybody with me?
Yeah.
Even if that were true, you'd want to say, oh yeah, that works, but it doesn't. Because this side over here still wouldn't have to be proportional, okay? It's not enough information. We would have to have the green and the red, not the red and the blue, being proportional sides if that's the angle, right? It has to be the included angle. So that one's no good. And obviously angle doesn't work because you only have one angle, right? So this one is, they can't be proved similar. Okay? Make sense? And this one's pretty obvious because not even the ratios worked out. So, okay, what about this one?
Side angle side.
Side angle side. Yeah. Everybody agree? Okay, now let's just make sure. Everybody, take a look, please. So I know that the vertical sides are proportional, right? Big to small is the ratio 2 to 1. Agreed? The horizontal sides are in the ratio 2, so the whole thing, the whole thing would be a 2 to 1 ratio, right? So those work, and both these, the small and the big triangles, share an angle. So side angle side. Make sense? Sides are twice as big, the including sides, and then these two sides and the included angles congruent. So, oops, yeah, that one. Boom, we got it. Okay, make sense?